and thanks for coming to watch my talk. I'm J.Delanoy, and I will present you with work that we did with my colleagues from the University of Zaragoza about editing material appearance in images. Well, first you might wonder, why do we actually care about material appearance? Well, the fact is, the way material look, and especially the material they're made of, the fact that an object is looking more or less glossy or more or less metallic, affects a lot the way we perceive such objects and the way we perceive the world around us in general. This scene that I'm showing here, for example, contains a lot of different materials, and all of them are creating this atmosphere, specific atmosphere in this scene. And if we change the material of objects, for example, making this lamp appear less glossy, it will definitely affect a lot how we perceive the scene in this example. But actually, how would you edit this image? Well, change the appearance of this object and make this lamp look less glossy in the image. Well, to do so, you would need to have access to some 3D definition of the scene and change the material in it. Well, unfortunately, for real images, usually you don't have access to a 3D definition of the scene. And even if you have access to it, then it's not clear how you need to modify the material such that you reach a certain appearance. It's unclear the effect of changing the properties of the material. Well, it is unclear the effect you will have in the final appearance when combined with the illumination and geometry of the scene. So the goal of our work is to allow such image editing in an intuitive way. So starting from an image that contains an isolated object with a uniform material, such as this one, we can give an appearance target. Here, for example, make the object look more metallic, and our methods output a new image that is depicting the same scene, but with now a change in appearance according to the target appearance. Well, obviously, we're not the first one. We're trying to modify material in images, but usually most approaches rely on inverse rendering, that is, decomposing the image into, for example, its material properties, geometry, and illumination, and then re-render the scene given those predicted properties. And then you can change, for example, the material and have a change in the final image. Well, unfortunately, first, this is a very difficult task because being able to robustly estimate all of those properties is very challenging. So it's hard to have such methods that really generalize to a lot of different scenes. And even if you manage to do so, well, again, how do you change the material parameters such that in this specific scene you reach a target change in appearance? So instead of relying on inverse rendering, we try to take advantage of human perception of material appearance. And it seems that our perception of material appearance is actually driven by image cues, such as, for example, the coverage, contrast, and sharpness of reflections that is linked to the glossiness of an object. So the idea is, can we manipulate this image cue such that we can reach, so we can change the appearance of the material? But unfortunately, there's not a single list of features that we can use. Perception is driven by a complex mixture of image cues that we have not identified yet. So we don't really have like simple sliders on features that we can change. But interestingly, recently neural networks have been shown to extract information that correlates well with human perception. Meaning neural networks have this ability to extract these very complex features that we use to perceive material appearance. And if so, then can we use neural network to edit the perceived appearance? If they're able to extract similar features, well, maybe we can also use them to change with image features. So that is the basis of our work. Our work relies on a combination of deep learning and perceptual data. So the core of our method is a neural network that will take as input an image and a target attribute and output an edited image. Then we can set the target attribute as, for example, a high glossiness score or a metallicness score or any other perceptual attribute we could have. Now we need to give a way for the network to learn how we perceive material appearance so that it's able to extract the right features that drive our perception of material appearance. And to do so, we will train our network with perceptually annotated data. So let's look a bit more to the data that we have. So we have images that are synthetic images or renderings that show a variety of different geometries under a variety of illuminations and materials. And for each of these images, we have a perceptual attribute values. So for example, for this image, we know that people have perceived it as much non-glossy and non-metallic. And these scores were collected through crowdsourced experiments. So what is the data that we have to train our network? What we don't have are ground truth pairs of images, meaning we don't know what this image should look like if we wanted to have the same scene with a metallic appearance. So we can't show the network directly a target image that it needs to reach, which makes the training complicated. So how can we use such data to train our network? Well, and before going to the training, I want just to go slightly deeper on the architecture of our network. So our network is a encoder-decoder architecture. So its first part is encoding the image into a Latin code that is a compact representation of the image. And that then we have a decoder part that will decode this compact encoding. Now we will add at this stage our target attribute value, for example, a high score of metallicness, and our decoder will take both the Latin code and the target attribute to decode and make the output image. Now what are the goals that we'll set to train this network? That we want to get some good quality images that depict the same content as the original one, but we also want the output image to depict the right attribute value. So let's first focus on the two first objectives. So these are very standard objectives for any generative network, so we use the same losses as many of them, namely a reconstruction loss to ensure that we're able to reconstruct the initial image when given the same perceptual attribute, and adversarial loss that guarantees that our images are indistinguishable from real ones, meaning they are of good quality. I don't want to go any further into details in this because, again, these are kind of standard losses for reconstruction. But using only this, well, our network will just simply ignore the input attribute and will just reconstruct the same image as the input one, whatever the attribute we put in the middle. So we need to have a way to enforce the attribute value in the output image, meaning how can we reach this third objective that we have here. Well, one of the first ideas that you can have is let's give some feedback to the network and check that the generated images are perceived with the right attribute. So we will add an attribute regressor on top of the output image that will predict the perceived attribute value of this image. Now the goal of the generator will be to try to have its generated images attribute well predicted by this network, meaning if I'm putting here a high metallicity score, then the attribute regressor should predict that this image will be perceived with a high metallicity score. Now how do we train this network so that it's able to predict how we will perceive the image? Well, it will be trained with the perceptual data that I talked about a bit earlier. So for each image we know how humans perceive them, so we'll just train it so that it reproduces the human ratings. With this trained correctly, we can reach this kind of images that I'm showing here. So it does look more metallic than the input one, but definitely not as much as what we would expect and what is the target that we have here. What is missing is some large-scale changes, meaning we have a few changes in like the reflections are a bit a bit more contrast, but we don't have this complete shift in appearance. And this is because we're only giving like pixel-wise feedback to the network. What we need to have to really have those large-scale changes is to act on the latent space of the network. This allows to really completely manipulate the image. So what can we do on the latent space so that we help to get this change in appearance? The idea here is that we will try to push the latent space to not encode any information about the input attribute. Meaning, if the latent code here does not contain any information about how metallic was the input image, then the network has no other choice as taking into account also the target attribute in order to reconstruct the right image. And that will give a good way of editing the image. Well, how can we manage to do so? How can we achieve this? We will add to our network a latent discriminator, but whose goal will be to predict the attribute of the image, looking only to its latent code representation. Now, the goal of the generator will be to prevent the latent discriminator from being able to guessing the attribute from the latent code. So if those two are trained correctly, our generator will learn to encode the image in such a way that it does not contain any information about the input attribute. And we will have reached our goal of getting a latent space that do not encode information about those perceptual attributes. So now if we combine this latent discriminator with our attribute regressor, we have something that can fulfill our third goal of getting the right attribute in the output image. And if you look at the output that we have here, we indeed have reached a very nice change in appearance. However, the image is kind of lacking some high frequency details. And not only in terms of reflection, but when like the geometry is not really defined in this image. Well, why is that? What happens is a very standard problem with encoder-decoder architecture is that you lose information about the image in the encoding process. And usually a way to solve this is to use skip connections that will forward features from the encoder part of the network to the decoder part, and that will transfer some high frequency information. Now remember that we're trying to shape the latent space to control its content, so we can't use skip connections. Otherwise, all of this information that we try to not include in the latent space will be forwarded, and we lose our shape editing. So how can we get high frequency details without using skip connections? The idea here will be to try to bring back some high frequency information, but only about the geometry and not about the material itself. And we will do this by the means of a normal map. This normal map will be added into the decoder, kind of in a similar way as skip connections are putting features from the encoder into the decoder part. This will allow us to get more details and especially to generalize better to different geometries. So that would allow us to really be able to treat a large variety of geometries. Unfortunately, it is actually not enough to reach the image that I'm showing here. And this is because we also need to make a choice about the architecture of the network. Either we have a network that is deeper and that has a compact editable latent space, and that allows to get this very nice change in appearance. Either we can have a shallower network that get a higher dimensional latent space that definitely allows to keep more high frequency details about the image, but in which it is very complicated to have this change in appearance and to control the latent space. So in order to take both the best of both worlds, we use a two-stage network. Actually, we have one first network that is a deep network that has this compact editable latent space and that is computing these large-scale changes in appearance. And then we have a second network that is shallower and that allows to, that will be preserving more high-frequency details. Then we will transfer features from the first network to the second one so that we transfer those large-scale changes in appearance into the second network, and at the end we obtain an image that is both containing this nice change of appearance, but also get more high frequency details. And that is the final image that we wanted to reach. Okay, so it's now time to look at some results on editing images. And first, let me quickly present you the images that I will use. So these are real images that we took either from online catalogs or that we photographed, objects that we photographed in various conditions. Well, first we automatically removed the background of this object. And then we used a normal map predictor to get the normal map associated to those objects. Remember, we need a normal map to make our network work. So here we train a standard image translation network, and this can even be seen actually as a branch of our network that first predicts the normal map before getting to editing the image. Now, what are the editing that we can get from these images? And first, we will look at some metallic editing. So these are the images that we'll use. In the three first ones, we're trying to reach high metallicity score. In the last one, we're trying to reach a low metallicity score. And these are the results that we obtain. So you can see that for the ones where we try to reach a high metallicity score, the network has, of course, increased the reflections. So the reflections are now covering a lot of the shapes that are very bright. But it has also changed the color of the object. So you see that there's some kind of a loss of saturation, and it definitely brings a sense of metallicity. And that is probably something that is linked to the fact that metal usually don't have a diffuse component. So the network here is in some way trying to remove the diffuse component from the original image. In the case where we want to decrease the metallicity, the network is decreasing the reflections, but also bringing back some diffuse color here. Now let's see what happens if we try to edit the glossy attribute. And in these two first images, we'll try to more increase the glossiness while we try to reduce it in the two last images. And these are the results that we obtain. So again, the network have created new reflections to bring a glossy look, or you have to try to remove the reflections to reach a matte look. But here you can see that there's no change in color. The color remains very similar in the edited image because the diffuse part has no change. You can have an object that is very glossy, but it still has a diffuse component. So it does not have this shift in color that is very specific to metallic appearance. And that's very interesting how the network have learned this difference between glossiness and metallicity, and I've learned what are these image cues that can really give a sense of a metallic object, of a non-metallic object, glossy or non-glossy. Of course, while our framework is not free of limitations, and the main ones that we have is this sensibility to the normal maps. So if the normal maps is noisy, but we will have some errors in the output, so it will be nice to find a way to get rid of this normal dependence. And remember that the normal map was bringing some high frequency information about the geometry, but we don't have any way to give information about the illumination, which means that it's hard to reach very sharp highlights because we don't know what is the illumination of the scene. So that brings very interesting tracks for the future to get either some kind of selective skip connection that will only forward high frequency information about what is needed, but also maybe make some link with modern neural rendering techniques that encode the scene in a very different way and in which we could edit the material appearance a bit differently. So that will be very interesting. So in order to conclude, we propose a framework that allows to edit images using perceptual attributes. So we have this link between neural networks and perceptual data, and we don't need any ground truth images to train our network. So we think this framework could be extended to other attributes, either related to material appearance or to other properties of images. And what it only requires is collecting good quality perceptual data from people. So that concludes my talk. Thanks a lot for your attention, and I will be answering questions during the conference.